Today we've got Dr. Penelope Boston joining us from just next door over at NASA Ames. She's the director of the NASA Astrobiology Institute, and we'll be here talking today a little bit about her research.
Great.
Cool. Welcome.
Thanks. Thanks, Calvin. I'm really happy to be here to share a few thoughts with everybody about one of the most challenging things that we're trying to do at NASA, and in fact, other space agencies around the world, and that is try to hunt for extraterrestrial life. And of course, we've been doing this for a number of decades, both within NASA, within the university, and research lab environment, and Europe is highly involved in this, and other countries are coming on board. Japan has a very active space program and a lot of interest in astrobiology, as do people in China and many other parts of the world. So this is really a global enterprise, but I'm going to give you really my own perspective on where the rubbing points are. Looking for life is extraordinarily difficult because life is not really a collection of stuff. It's a collection of stuff that is actually behaving in the time dimension. So it's an ongoing process. And this means that it is, at one sense, flamboyant. We live on a planet that's absolutely saturated with life. Our planet is dominated by life. But if we have life on other bodies in our solar system, it clearly isn't the same kind of global dominating force that it is here. And so this really changes the game. And a lot of the work that those of us in the science community have done on this have to do with looking at examples that we have on this planet that are very challenging. So marginal environments, extreme environments on our planet has really sort of set the stage for trying to expand our thinking in that regard. We really want a tricorder where you just point your device at something and it tells you a bunch of wonderful stuff. But we actually really are still fumbling around in many cases with more like a Rube Goldberg device. And this is the cartoon that actually started the idea of these crazy devices that Rube Goldberg, who's a famous artist and cartoonist, actually came up with back in the 1930s. So we often refer to Rube Goldberg devices as some kind of kludged together thing. So even though we have many wonderful technologies that we are working with, because life is a subtle phenomenon, and we don't know what it's going to be made of on other planets, and we don't know even what its pace of life and many other things about it are actually going to be like, we are trying to design instrumentation and protocols and accessibility to places that we are tremendously unfamiliar with, and where the life might be so different in its many different properties that trying to even recognize it as life might be very challenging. Now, it could go the other way. It could be that there's something so optimized about the way our life does chemistry that it's the only road available. I don't personally believe that, but there are people who do believe that. But really, these are articles of faith at this point rather than really informed stances. So that's the background. So what are we looking for? Well, we're looking for things that are still alive. If they were cute and green with 3 eyes like these guys from the movies, that would be easy. The truth is that they're much more likely to be microbial organisms. And one of the reasons that we think so, of course, is because really for 3/4 of the time that we have evidence of life on our planet, in the rock record, it was microbial life. Big things like us were decorative additional afterthoughts that happened after many different cycles of geological changes had occurred over hundreds and hundreds of millions of years, billions of years. So it wasn't until between 700 and 800 million years ago that what we would now call complicated multicellular things began to be evolving. And this is on a planet where we have evidence of life back to at least 3.6, possibly 3.7, and possibly 3.8, depending evidence from that period of time is really subtle and really hard to interpret. But anyway, the bottom line is it was a heck of a lot longer ago than we have big things. So this pushes us into the realm of microbiology. On the other end of the spectrum, of course, we are also looking for evidences of past life. And I don't know if there are any amateur paleontologists in the room, but if so, you'll know that the way you look for fossil material is very different from the way you study living material. And yet we have both of these twin goals because we don't know what we're going to find. And even though we would all love to find actively living organisms somewhere in our solar system, we'd still be very happy if we found convincing evidence of even past life, for example, on Mars. So one of the biggest problems is that if you take a physics and a chemistry perspective, this is very instructive, except that life is really not a package of bulk properties. So in many cases, we are measuring bulk properties of a planet. And by bulk, I don't mean things the size of California. I mean bulk things that are above the microbial scale. So microorganisms are individually very tiny, although they can be macroscopically visible in the aggregate. But in very low nutrient environments where the numbers of organisms are very low, you have patchy distributions that are hard to explain. You know, the obvious thing is if you have a nutrient gradient, you would expect organisms to be arrayed along that nutrient gradient. And there is some of that, but there's also more magical properties that life has, which seem to have something to do with self-organizing properties of complex systems. And they do not just, trivially map onto what is available for them. And this is something that a number of folks in the community are studying, but we really don't have a grasp of it. So why am I talking to you about this, other than that I'm working at NASA currently? I have spent most of my career working in extreme environments. And for the past 25 years or so, I have focused primarily on the subsurface in natural caves and mines. I'm not going to spend a lot of time on my work, but I just want to show you a few examples, some of our more photogenic examples, that try to look at the most extreme physical and chemical conditions that we can find on our planet in an environment in the subsurface where photosynthesis is not possible. So our focus has always been on the microorganisms that make their living not off organic materials, but off inorganic materials. They're essentially rock eaters. And they get their various energy quantum by doing things like oxidizing metals in minerals. So this is a geologically driven source of energy for these organisms. And as we look around our solar system, we see nowhere else that is green and gooey like our planet. And so the fact that we have photosynthesis as our primary driver of the energy that goes to run our biosphere is very lucky for us. That's why we're all sitting here. But on a planet with a much more subdued potential biology, we're not going to see that. And we know that we don't have anywhere else like Earth that we can find in our solar system. So we're looking for much more subtle, much lower biomass systems, perhaps functioning at a much slower level. So we go places like in the upper left-hand corner. This is a cave that we have studied in Tabasco, Mexico for almost 20 years now, starting in 1998. And this system is dominated by sulfuric acid. It has hydrogen sulfide pouring into it from a number of springs, and that goes into reaction with oxygen in the system, in the water, and in the air, and produces sulfuric acid. So it's a hyperacidic environment, and that's why we're all duded up in the suits and so forth, and the breathing masks and auxiliary oxygen bottles so that we can actually survive in there long enough to do the work. That's actually very chemically extreme. It's not temperature extreme. So if you go to the upper right-hand side, you can see that we're working in another environment. This is a much newer project on the flanks of Mount Rainier, There's a lot of mountaineering involved in getting up there. There are permanent ice caves that are the result of being in an icy environment, but these are volcanic fumaroles. Mount Rainier, of course, is a very large and gorgeous volcano that is definitely still active, although it hasn't erupted in a good long time, but it will again someday. And in the meantime, it's got a lot of the similar gases, but these are coming out into a very cold environment. And then the lower left has been the focus of a lot of National Geographic expeditions that we have been part of, and we have explored these giant crystals in a very hot environment. So this is on the order of between 40 and 60 Celsius. The hottest that we've had in there is in excess of 60 degrees C, to the point where one of my former graduate students got second-degree burns when one of her boots ruptured. So that's pushing in the very hot direction. There are things in the subsurface of Earth that are unsuspected in the surface, and so it's almost like going to another planet every time you go into one of these extraordinary environments. And that has been very helpful in my own thinking about imagining these different kinds of conditions combined in various different ways, and how we would go about actually trying to find these in alien terrain, and certainly robotically for the foreseeable future. Ultimately, perhaps we'll have humans on Mars that can actually do some of this exploration, but for a good long time, we're not going to be able to do it other than with our devices that we send there. So this is a wordy slide, but I want you to really focus on the colored words. These are the high-level things. So we talk about biosignatures, meaning anything that life leaves behind. And this can be as subtle as metabolically produced gases that you see here in this list. Obviously, the gold standard would be if we could actually find live organisms, but much more subtle accumulations of suggestive biological molecules that we know are part of our biology here. Possibly molecular fossils. These are traces of organic materials that we know, at least on Earth, are associated with various different kinds of organisms, might be preserved in things like silicate materials or carbonates. And of course, if we find true fossils, they're known as body fossils, that are somehow recognizable by their structure, and not an artificial mimic of a form of life, that would be obviously the most strong type of evidence. But there are many other things that we see on Earth that are the result of life, including biominerals that are produced by the activity of these rock-eating and mineral-pooping-out organisms that I was just mentioning. And then other subtle geochemical traces that I will not go into the nitty-gritty details. Well, on my lithometer on the left-hand side, you can see I've got sort of a slider bar from extant life to extinct life. So all these different kinds of pieces of evidence either pertain more to the extinct life end of that spectrum and more to the extant life, guys that are still alive. So the truth is about our current grasp on life detection that we're really doing it by circumstantial evidence. We are looking at some of those weaker lines of evidence that I just quickly flashed before you in the previous slide, and looking for places where we may find complicated organic compounds, and I don't mean just simple amino acids, I mean things that are more complex that we can imagine being a product of life, and the co-location of those, or patterns of molecular or even suspicious patterns of elemental abundances in one place. But that's really still forensically a circumstantial piece of evidence, right? None of those things are really the clinchers. You could go, gee, that looks really suspicious, but if it isn't wiggling around, you don't really know that it's life without a whole lot more work. On the other hand, of course, it's very hard to find complicated structures. So this particular electron micrograph that you see there is from one of our lava tube caves that we've studied, and they're pretty convincing. They're fuzzy. They look sort of like little chrysanthemums to me, although each one of those is about a micrometer in diameter, so you could fit 100 of those across the diameter of one of your hairs. So very, very tiny. And they appear in very patchy distributions in this lava tube because there isn't a whole lot for them to eat. So what are our chances of being able to look at enough material on a robotic mission to actually come up with those? So you can begin to see this conundrum. We've got various different lines of evidence that we need, but trying to get them all on the same sample or in the same time is really challenging. So I just show this as an example of the work of one of my colleagues, and in fact, one of the team members of one of our NASA Astrobiology Institute teams happens to be the one that is headed out of SETI right here. And Richard spends a lot of his time worrying about how we're going to do life detection and has come up with steps towards one of these analytical combinations. And we're not going to go through this in detail, but just to point out that he's trying to combine microfluidics to actually get access to microorganism sized creatures, and at the same time use fluorescence to try to look for living materials. Very often, of course, we look for natural fluorescence, or we look for fluorescence that we can actually induce by using various wavelengths, or in fact even putting materials into the sample that will bind with biological compounds. So we're making a lot of progress in these lines, but even this is not really a life detection. It is still piecing together tiny bits of information about the chemistry and hoping. This is real life detection. If something was big and it came up and bit you on the ankle, that would be pretty convincing. And anything short of that is much less convincing. And so the question for us is, what is the suite of things that we need? How many different lines of evidence do we need? And how strong does that evidence have to be to actually convince us at some time in the future that we've found an actual living creature? Well, this is not new. This is a famous cartoon from the New Yorker that was drawn in 1962, very early on in the space age. And the fundamental principles of what we need to do are still the same. It's really hard, but we spend a lot of time trying to figure out what life forms you might get from first principles given whatever properties you know about a particular body. So for example, Mars. We've had a long history of attempting to look for life on Mars. Our first attempts in the early to mid 1970s were very naive in retrospect. We didn't know that. This was before we'd even discovered that there were hydrothermal vents at the bottom of the oceans, right? We did not know about the world of extremophiles at that time, but we did know that maybe on a planet there would be a very different atmosphere, and the creatures there would be using that. So that notion is one that has been in people's minds for a long time. So I just want to share with you some of my biggest concerns, and where I hope that not only folks within NASA and the university communities, but everybody within the tech realm that might be interested in some of these issues could find a way to contribute. So these are the 5 biggest problems that I see right now. Simultaneous measurements. You would think we would have solved this. We haven't. In terms of doing the kind of biology that we do in extreme environments or any environment on Earth. We have missions that don't last that long. And if they do last long, we go to different places. So the idea of long-term observations to capture changes in things that might be alive, that may be living on a very, very slow time scale and growing very, very occasionally, perhaps once every 100 years, perhaps once every 10,000 years. And we have examples of that in the Antarctic, even on our own planet. The doubling time for cells that are living under sandstone, in sandstones in the Antarctic dry valleys, probably only reproduce once every 20,000 years. Well, that's pretty darn hard to capture that anywhere, and certainly on another planet. So how do we solve that problem? Problem 3 is access to challenging terrains. Well, it's robots. I love robots. And there's a wonderful community of robot designers that are coming up with concepts that are, certainly the kinds of things that we're going to need, and yet what are we still flying? We're flying Mini Coopers, basically. Okay, so we have to close the gap of trying to be able to do tech demos and actually vet these kinds of much more creative and much more capable robotic capabilities before we can fly them. What you do on Earth is one thing, but getting something ready to be approved for space flight is a whole other thing. It's vastly more difficult, it's vastly more expensive. Problem 4 is essentially seeing like a human, and by that I mean sensing and integrating at the same time. Particularly for the icy moons around the gas giants where we know that there are liquid interiors of these, and where there's a huge amount of circumstantial hope and evidence that these would be very habitable places on the interior. We cannot direct these immediately on a step-by-step basis from Earth. It's hard enough with Mars in terms of the delay in the return time of commanding spacecraft and commanding payloads. When you get out to the orbits of Saturn and Jupiter, the delay time just makes that ridiculous. And in fact, the interference from the radiation environments, these high radiation environments in the gas giants, and the fact that wherever you're interrogating is going to be eclipsed by the planet episodes and so forth, that fluidity of communication that you need to actually run things from the ground is simply not going to be there. And this, of course, pushes us in the direction of devices that can make their own decisions. And then binding all these together is a thing called planetary protection. I don't know how many of you have ever heard of this term. It is not planetary defense, which is a related term that NASA has interests in. That's when we're thinking about near-Earth asteroids slamming into us, and what are we going to do about that? This is on the other end of the spectrum, and this has to do with microbiology. And this is a problem that was recognized right at the dawn of the space age and before, and that is microbial life could potentially be a hazard to any life on another planet if it comes from here. And then in turn, the reverse is also true, and that is as we get to the era where we're bringing back samples from astrobiology targets like Mars, we want to make sure that we are not risking any adverse consequences for our own one and only home planet. So these are very serious issues, and they have been taken very seriously. NASA has a planetary protection officer in office that worries about this. There is an international body called COSPAR that brings together the global space community, and one of its divisions, of course, is devoted to planetary protection. And in fact, this year, the COSPAR meeting this summer is actually going to be down in the Pasadena area in Southern California. It travels all over the world. The last one was in Turkey, was intended to be in Turkey, and that was just as the coup happened. So that one was canceled. But this is a body that deals with a lot of interactions, and it deals with this problem of how do we make sure that we're not screwing up somebody else's planet and that we're not screwing up our own. So this is a very serious problem. So just a few details. The simultaneous measurements, we've got a lot of signal-to-noise problems. It doesn't matter what kind of planet it is, we've got issues with both of these. We're looking at patchiness that we don't understand, as I mentioned before, low biomass probably. The life might be very cryptic, that is not recognizable to us, and they might thrash around at a very, very slow pace compared to us. And the minute you take a microbial sample, even here on Earth, you have changed it. And we try to compensate for that here on Earth because we understand a lot more about our own biology. But we have found that a problem in extreme environments where we are poking around at things that We don't know who's there. We don't know how many are there. It all looks like minerals or soil or something. It's only after a significant amount of work that you can actually prove that some of these things are alive. And some of those examples I show here from some of our previous work. The stars that you see on the interior of each one of those manganese oxide stars is a tiny microorganism, and it causes the precipitation of that manganese oxide as a byproduct of using other oxidation states of manganese minerals to make its living. And it produces these characteristic things. I can't tell you how many times this kind of work has to be submitted before you can prove to yourself and other people that you're really looking at a living thing, because from the surface it just looks like a mineral. The other end of the scale is we see things here on Earth that we cannot determine what they are. And I show this thing that looks like a broken mesh stocking. And we have found these kinds of structures literally all over the world in every kind of geochemistry and every kind of temperature in caves in the subsurface. And after 20 years of working on this, we still don't know what they are. They don't map onto any other kind of microorganism. So even here, we essentially are working with aliens in a way. So the solution to this is really that we need simultaneous multispectral and multiscale imaging, and we need to have that done at the same time we're actually interrogating the chemistry, and preferably something about the energy state to look at what the entropic condition is within a suspected organism, and all at the same scale that matters to microorganisms, which is really very tiny. It doesn't do you any good to look at one size of a hand sample rock on Mars for one thing, and the other side for another thing, and the other side for another thing. You cannot then overcome that logical conundrum of bringing those together to really produce highly trustable, high-quality data that would convince us that it was alive. One of the things that may be helping us with this problem is relatively new, and it's the idea of not big spacecraft, but whole fleets of tiny little things. So here again, we've got the cryptic life problem. Are they even recognizable? Low biomass again, slow pace of life. You can't invade them with clumsy sample handling because you might suppress them or destroy them. And we even have large-scale patterns changing on geological timescales, or perhaps a little shorter. And the upper image shows one of the patterns that we've been working in. If you look, this is the sulfuric acid cave in Mexico. If you look at all the dark material, you can see that it looks like little dots. It's actually a hieroglyphic-like pattern. And this is something that is a self-organizing property of microbial communities, which helps them distribute fluid flow and the distribution of nutrients and other limiting factors. We've been working on the mathematics of the development of this, and then trying to back what that means out scientifically from that work. So we have all of these complicated things. The Poofball Sea, which happens to be in a cave in southeast Alaska, right around freezing, the white stuff that the hand is pointing to, that's actually a shallow pool. And those poof balls actually are composed of previously undescribed filamentous microorganisms that produce these beautiful fin-shaped calcium carbonate crystals that you see in there. Well, we've never seen anything like that before. And trying to look for that life signal when your visual appearance of these poof balls are actually globs of fluffy minerals. So I show these pictures just to show you pretty how challenging this is, even here. So we really need long-term monitoring, and we are looking at things like small sats, smart breadcrumbs, we don't know. We need things that are self-contained. They don't have to do a lot, but numerosity can overcome this problem of time dimension, and it can also give us the basis for a statistical analysis. If we can't sit there for 20,000 years, we can do a statistical analysis of various phenomena, and that will give us insight into some of these. Well, now we get to the robots, which I love. I have made a cottage industry before I went back into NASA when I was still in the university environment of essentially being the pet astrobiologist of a lot of robot groups. So MIT and JPL and various other ones, because people who are designing these wonderful robots, they need to know what the customer base wants, and I am a customer, and a very chatty customer, and I love robots. So we want to be able to get into these difficult terrains. In my case, it's caves and rock overhangs and things like that, but even rugged terrain on the surface of Enceladus, for example, or Europa. We have nothing that can do that at this point. We need to be able to look at features of significance. So RSLs are these recurring slope linei, these streaky things that come and go on Mars and appear to be brine or not. Okay, we don't even know what they are. Maybe they're liquid and maybe they're not liquid. So we have to be able to get up to those with robotic devices that we can then remove and do the analysis. We want to be able to interrogate tiny environments and huge environments and sensitive environments. And the way to do that is with surrogates that are our robotic partners. Biologically sensitive environments, even with astronauts on site, these planetary protection protocols, these planetary protection concerns, means that it's not going to be like The Martian, where the guy is tromping around on Mars and walking up to things and practically licking them. I mean, I know he was trying to stay alive, but that's not the way to do science. So that was a great adventure story, but it's not the way to do astrobiology on Mars with astronauts. And so we need surrogates to be able to go do that. So one of the frustrations that I have, and I know a lot of folks have, is that we really need to enhance the pace of being able to field test these access robots and other ways of expanding our ability to detect the environment. And we need to be able to fly some of these on tech demos. Spaceflight is really expensive. There is intense competition for everything that goes on a spacecraft. And so it's a big scramble to try to get new devices that are still untested in terms of actually going to another planet or even flying on a spacecraft. And so this is really important. Nested multi-unit designs where you've essentially got something like we proposed many years ago. We called it Mother Goose, and it was a mother robot, and then we called it the egg crate, which is where all the little tiny individual robotic units were going to be housed. And at the time we were using artificial polymer muscle activated hopping mechanism for these little spheres. That was an MIT collaboration that we did. But there are many other ways to do this, and we have to solve this problem. One of our big talents as humans is seamlessly putting things together and coming up with creative solutions. And our ability to do subcognitive pattern recognition, we don't even know how we do it. I know that there are a lot of folks in the community at large that are trying to mimic this or emulate it, perhaps is a better word. We need this, and really the direction that we have to go is in machine learning and pattern recognition, and coupling that to our devices being able to make real-time decisions in the scientific context. They have to be our surrogates more than just in mobility. They have to make decisions about which of their tools to deploy. We cannot tell them everything. We can help them. We can be with them as a virtual reality presentation, perhaps, but we need them to be us in some of these environments, and we are not even close. This is one area that I'm hoping Silicon Valley will magically help with, even though, of course, we have folks in NASA who are working on it too. So this is an area of very active interest in collaboration. And then things that we can't directly sense, magnetic fields, chemical gradients, all these things that we do not sense because it's not part of our particular biological history. So capturing that pattern recognition and machine learning technology, and then really trying it out in some of these environments that I showed you that we work in here, that connection is very loose. It's expensive to do that. Extreme environment expeditions are expensive enough to begin with, and then when you're taking prototype technology out there where it's breaking down all the time, these are very, very complicated. And one of the issues is that it's very hard to get enough money to do one of these projects right. And then the last problem, of course, is this planetary protection. If you do not do this well, you enhance the signal-to-noise problem in terms of looking for rare life in an extreme environment on another planet. If you find it, and it's very similar to us in chemistry, and you have not done the planetary protection well, you have broken that logical chain where you can actually cleanly claim that what you have found is extraterrestrial. Maybe it's contamination you took with you. So there is a scientific rationale, and then there is a deep ecology rationale, which is you don't want to threaten another biosphere. NASA focuses heavily on the science aspect and leaves the ethical aspect to others. But many of us within the agency and in the community, of course, are very concerned. We're all conservation-minded. We value our own biosphere as well as everybody else's. One of the problems that we have is that between the time that we actually flew the Viking missions to Mars and now, we've had fabulous developments in electronics and all kinds of materials and engineering components. The problem is for spaceflight to biologically sensitive potential targets, those have not been developed with an eye to how they can actually be sterilized. You can't stick everything in a heat and pressure chamber like an autoclave and have that device survive and still function. So we have fundamental incompatibilities between the classic ways that we sterilize things as microbiologists on Earth, and the other aspect is we have to also have ultra clean conditions. So it's not enough to just kill off anything that is there. You also have to have your spacecraft scrupulously clean so that here again you don't get a signal to noise problem. You don't get contamination even if you're not looking for life. Even your devices that are looking for the background chemistry, the mineralogy, still cannot be interfered with an unclean spacecraft. And of course, I'm sure you know that spacecraft get cleaned within an inch of their life, whether they're sterilized or not, right? So the ways people do these two things are not compatible. People have said often, oh, gee, why don't you just go to the, the BLS-4 containment facilities at the, Center for Disease Control areas where they work on stuff like Ebola and so forth. Well, that's great for the sterilization and working with, organisms, but it isn't going to clean things up for you at all. CDC facilities in terms of spacecraft cleanliness are pigsties, right? So it's not the same thing, and these have not been worked together. So I'm not going to go through these, but just so you know, we have a lot of tools, right? We have the heat, dry heat, steam heat. We can beat the dickens out of things mechanically. We can use all kinds of gases and so forth to chemically sterilize. We can smack it with various kinds of radiation. But how do you assure that all of those different things are compatible within subsystems of devices, supersystems of devices, or even, indeed the whole spacecraft? So it becomes a massive, complex systems engineering problem for which we have not tooled up. And so therefore, the planetary protection protocols that are implemented now are unreasonably expensive in many cases. They really can be an impediment to spacecraft. We've seen this play out with our upcoming Mars 2020 mission, trying to meet all the demands of planetary protection while at the same time using components that are of mixed materials and trying to put all these things together. It's very complicated. And frankly, we're just not masters of the art of this. And so that has cost consequences, which means we can't go as many places. So we really need a sea change, and this is gradually happening, but it's very slow because people are used to doing things the way they're used to doing them, right? So my preferred solution is that we design these planetary protection requirements in as high-level engineering requirements. You don't add them on at the end where it's really expensive. It's like if you're building a house and you've got 2 bathrooms planned, and when they're about to start putting up the drywall, you go, you know, I really think we need a 3rd guest bathroom. That's like the worst way you can build a house, right? And it's precisely analogous to the way we have to put spacecraft together. There are many things that have not been tried, and I list a couple of them down here. So the cruise phase, while you're actually in space, getting to wherever you're going, can you have ways to re-sterilize those components while you're actually flying, while you're in a non-biological environment? Use of new materials that might facilitate either trapping microorganisms and immobilizing them, or killing them and causing them to mineralize to CO2 and water, who knows? But those things are on the horizon, and we need to explore that. So if we are able to stumble our way forward with a measure of good sense and cleverness, serendipity, and synergy, and solve these problems, then we stand a much better chance of finding life on these missions that cost a lot of money. It costs at least $1 billion just for the bus ticket to get out to the outer solar system. That's just to get there. That's not the payload or anything you're going to do. You could send a brick that far, and it would cost that much. So let me come back to the original theme, and that's the tricorder. Can we really develop it? Well, maybe over time. We're willing to settle for something much less developed than the science fiction version. One of the things that may be called for in a proposal call fairly soon is the baby step of taking an imaging capability and a significant chemistry capability and melding those into a conjoined unit to do 2 things well without interfering with each other in the same device. So that's the level at which we find ourselves. I've tried to paint a picture for you of where I think we need to go. So are we ready to go find life on Europa? We're ready to go look at some of the habitability properties of Europa, but we are not ready yet for the life detection. So this is the kind of growth area within technology that provides us with a unique and fascinating problem to have people exercise their brain cells and come up with solutions. But all of the things that I've described have real-world applications. The ability to detect life obviously has many applications in terms of detecting pathogens against a background that's biologically rich, against a background that's biologically poor, for national defense or terrorism circumstances, epidemics, things of that sort. So this is not simply only devoted to this main exciting core function that we have within NASA, which is exploration of our universe and the search for life amongst that exploration. But it also is something that can act as a major technology driver. And with that, I'll end. Thank you. And I'm happy to take questions if there are any.
Thank you. So you've painted a very kind of broad and diverse picture of what life can be, and even if we just look at the kind of organic chemistry of life, is like such a spectrum from simple, amino acids, complex proteins, all the way through to complex life. And kind of, I guess, on Earth, it's been easy in the past to say, okay, once it's life that we recognise, then we can kind of go from there.
That's right.
If we're now kind of broadening that, do you think there could be life on Earth that we haven't recognised as life yet?
That has been suggested. I don't know if you're familiar with the work that Paul Davies, who's a physicist at University of Arizona. He's a very creative guy, and he's suggested that maybe there's a shadow biosphere, that we actually have organisms here that we are not detecting because they're so different from us. I don't know what to think about that. I mean, I can argue it either way. If it is something very different from us, our ability to recognize it is clearly, we're biased against it. On the other hand, there are ecological principles that have been developed by observation of 150 years of biological development. One of them is called the competitive exclusion principle. I don't know whether that applies to whole classes of organisms. I mean, the idea of that principle is that any two species, if they're competing for exactly the same niche, somebody will lose and somebody will win over time. Is that always true? Can that be balanced? Are there circumstances where those could be symbiotic relationships? Or is it as if you have a superimposed system that is so different and is not tapping into the same resources, so there actually is no interactivity, in which case, then maybe. Actually, Steve Benner, who was one of the people who's involved in a National Research Council study that was done a number of years ago. It had a big, long official name, but we all call it the Weird Life Study. And they were looking at those issues, how out there could life be and us still detect it? So could it be made out of silicon? Could it be organic materials that we know, but with anhydrous ammonia as the solvent? Could it be solid state? Could it be all these other things that we are not? And so we're still at the very much speculative stage. So I think actually modeling might, ecological modeling might actually give us more insight than what we can actually observe. Paul Davies and Steve Benner, may be right about a shadow biosphere, or it may be just notional. I think that if anybody stands a chance of finding something like that, it's people like us who are in weird environments where we see things. I showed you the weird mesh stocking thing. We don't know whether that has DNA. We don't know because we're looking at it against a background of other organisms. So when we do the genetics, we get this long list of strains that are not known to science. If you can't grow them, and I've been trying to grow them for a long time and have failed, I don't know who they are. So, maybe they're made out of non-DNA. I don't know yet. So it's a very slow process. So that's a long-winded answer to your question, but it's a very profound question. Yeah, thanks. Great.
Thanks a lot.
Yeah, my pleasure. Thanks.